Hello everyone, and welcome back to C++ Real-Time Audio Programming with Bela. I'm Andrew McPherson, one of the original creators of Bela, and for those just joining us, this is a class about creating the components of synths and audio effects on embedded hardware using the C++ programming language. Specifically, we cover a number of programming topics, each of which is associated with one or more music and audio topics. For this lecture, we're going to look at working with buffers and arrays, and we're going to look at this in the context of creating a wavetable oscillator. So over the course of this lecture, what you'll learn is about working with buffers and arrays in C++. We'll look at interpolation as a way of getting a higher quality output from a limited size buffer. And we'll also look at how to use Bela's built-in browser-based oscilloscope to visualize signals from your code. What you'll make by the end of this lecture is a wavetable oscillator, which is a form of oscillator that can produce a number of different waveforms. You can find companion materials, including code examples, for this lecture on our GitHub page, link at the bottom of this screen. To follow along with these examples, you'll need a Bela kit. That can be either a standard Bela starter kit or a Bela mini starter kit. For some of the lectures, though not this one, you'll also need a few other bits of electronic components. Details about this are on the companion materials on the GitHub page. In the last lecture, we looked at the Bela C++ API, and we saw that you had to implement three main functions in a Bela program. One of them is called setup. It runs once at the beginning, and you use it to do any initialization that your program requires, for example, allocating memory or loading files off of the disk. The main function that you need to implement is called render. Render is what we call an audio callback function. The Bela system will call your render function once per audio block. If you want to learn more about block-based audio processing, go back to lecture 1 in this series. But the main idea is that every time the render function runs, your job is to generate a short snippet of audio and return as quickly as possible so that the Bela system can handle the rest. Finally, your program should implement a function called cleanup. This runs once at the end of the program, and you would use it to release any resources that you might have allocated in setup. In the last lecture, we looked at what it takes to play a clip of recorded audio which we had loaded from a WAV file. The sound, once it was loaded, was stored in a buffer, which in C++ was basically just an array, a series of values ordered one after another in memory. Now, the issue that we had last time was that the buffer containing the sound was almost certainly longer than the block size of our real-time system, and so we had a challenge copying the buffer block by block into our real-time audio output. And the problem that we had was that we needed to keep track of where we left off at the end of each call to render. Now, this challenge of remembering where we are within an audio file should be a familiar one from digital audio editors. And in fact, we see it in the form of the playhead. Any audio editor will show you a vertical line which shows you where within the sound file you're playing at that given moment. And we essentially need to keep track of something very similar to remember where within the audio buffer we are playing from. So from a programming perspective, we call this a read pointer. The read pointer is essentially just a number or an index which tells us where in the buffer we're playing from at this immediate moment. And it works sort of like the phase of an oscillator, where we need to remember where we left off so that at the beginning of the next call to render, we pick up from the right place. The upshot was that the read pointer, like the source audio buffer itself, needs to be a global variable so it doesn't forget its value. And as we play the file, we don't actually change the contents of the buffer. What we do instead is have the read pointer move to keep track of where we're playing from at any given point in time. As we saw in the last lecture, this created something of a challenge in keeping track of the various buffers and indexes that were running around. Just to summarize briefly here, we had essentially two pointers or indexes that we were interested in. One was the read pointer, which looks inside of the source buffer, which holds the whole sound, and then we had this other index, which we called n, which was essentially keeping track of where we were within the buffer of that particular audio block, i.e. that particular call to the render function. And so what would happen is the first time we called the render function, the value of n would go from 0 to 7, while the read pointer also went from 0 to 7. Here we're assuming that we have a block size of 8 samples for purpose of illustration. So the first call to render would run something like this. The samples would be copied from the source buffer into the real-time buffer, the render function would finish, and the Bela system would play that sound. The next time render was called, n would go back to 0 again, but g read pointer would remember where it left off. In this case, it would start at a value of 8. So when this render function runs, we would copy the samples from 8 to 15 into this particular audio block. The render function would finish, those would be played, and then render would be called again. This time n goes back to 0 once again, g read pointer starts at a value of 16, and so forth. And so what's happening is that the render function is copying the source buffer into the Bela real-time audio output, block by block, as we go along. And the key was remembering where we left off, which is that green read pointer. Here's the code that implemented that particular mechanism. You can see at the top that we had some global variables which kept track of our buffer of samples, and of the read pointer which told us where we were playing from. And here within the render function we had this for loop. This for loop runs once per sample within the block. Although in the previous slides we were using a block size of 8 just to make things fit on the slides, the default Bela block size is 16 samples per block. Within this, we saw that we used the value of n to keep track of where we were writing the audio sample within that particular real-time block of Bela. The value of n had to be between 0 and 15 if we had 16 elements in the real-time block. At the same time, we were reading from the source buffer at the read pointer, and the read pointer, by way of being a global variable, is going to remember its value from one call to render to the next. This is where we were updating the read pointer, and notice that when we get to the end of the buffer, we wrap it around back to 0 so we don't fall off the end of our array and crash our program. There's another name for playing a buffer of samples over and over again in a loop, and that is a wavetable. Essentially, we are building an oscillator by playing a buffer of samples that represent one oscillation of a signal over and over again. So this is an alternative to calculating the value of an oscillator mathematically using a function like sine, for example. Essentially, instead, we look it up from a table that we have pre-computed and stored in this buffer. So there are some advantages of using a wavetable over a function like sine. The first is that using a wavetable can potentially take less computation, because we can just look up the values from a table rather than having to run the sine function every time. Another advantage is that we can have more flexibility in the wave shape. Because we don't need to find an explicit mathematical formula to compute each sample, we could simply load in the wavetable from a file or some other form of storage. So this is what we're going to work on today. And what we need to figure out is how to take the terminology that we used in the context of oscillators in Lecture 1 and adapt it for making a wavetable oscillator here. Now you might remember from Lecture 1 that we had to save the phase from one call to render to the next, and so we stored it in a global variable. We have an analogous situation here where we need to keep track of the read pointer, which is pointing somewhere in our wavetable buffer, and we are going to need to remember that between calls to render. In Lecture 1, we saw that the phase of the sine function was analogous to the angle around the unit circle, and the sine function itself would give us the y, or vertical coordinate, of that particular angle on the unit circle. So our analogy in the wavetable case is that as we would spin around the circle, we are going to move the read pointer from the beginning to the end of the buffer, like this. So notice that the time it takes to make one complete pass through the wavetable buffer is the same as the time it takes to spin once around the unit circle. So, if that's the case, then what determines the frequency of the wavetable oscillator? Well, when we looked at the original sine oscillator, we saw that the frequency was the derivative, or the rate of change, of the phase over time. So analogously here, the frequency of the wavetable oscillator is going to be given by the rate of change of the read pointer. That is to say, how far does the read pointer advance every sample? Now, if we look back to the previous lecture, where we played a sound file in a loop, we saw that g read pointer always moved at a rate of 1 sample per sample, i.e. every time we read a sample from the buffer, we incremented g read pointer by 1 and wrapped it around at the end. The problem that we're going to have here is that we want to have the wavetable oscillator have an adjustable frequency. What that means is that g read pointer is going to need to increment at a different rate depending on what frequency we want it to be. So what you're going to need to do in the coding task just coming up is to figure out how much to increment g read pointer each time to have it play the oscillator at the right frequency. And my hint to you is to go back and look at the calculations in the original sine oscillator from Lecture 1 and think about what would replace the factor of 2 pi there. So this brings us to our first task. There is in the companion materials for this lecture an example called Wavetable. You can download that zip file, drag it into your browser, and it should prompt you to make a project with the name Wavetable. This wavetable example implements a triangle wave. if you run the project without making any changes, you should hear a triangle wave, but it'll be at the wrong frequency, like this. But what we want to get to, once our code is doing the right thing, is a frequency like this. So pause the video here and see if you can work out what you need to do with G-read pointer to make the frequency correct. So perhaps you got a chance just now to make that code work as expected. In case not, here's a hint to work with. Our previous example of a sine oscillator calculated x of n as the sine of phi, where phi represents the phase. And what we did was, after each sample, we incremented phi by a value of 2 pi times f divided by fs. So f here is the frequency of the oscillator, and f sub s is the sample rate of the board. So in this case, that would be 220 Hz and 44,100 Hz respectively. And in this case, the valid range for phi would be greater than or equal to 0 and strictly less than 2 pi. Once we get to 2 pi, we wrap back around to 0. Okay, here's our new approach with the wavetable. What we're saying instead is that x of n is equal to the wavetable of phi, where phi this time is going to represent the read pointer, or the place within the table that we want to read. Now, in this new case, the range is not between 0 and 2 pi, it's actually between 0 and the length of the buffer, or the length of the wavetable. So, what is the update expression then that we need? Instead of phi is equal to phi plus 2 pi f over fs, we're going to do this. Phi is equal to phi plus the length of the table times f divided by fs. So perhaps this is enough of a hint if you haven't previously completed the example and want to try it again now. Pause the video again here, and then we'll look at the code. Okay, so here we have an almost complete, but not quite working example for the wavetable oscillator code. The line in bold is the one that updates the read pointer according to the calculation that you see at the top of the slide. So that equation there and that line of code correspond to one another. And remember that the plus equal operator means G-read pointer is equal to itself plus something. And if you want to learn more about this structure called context and its constituent parts like audio sample rate, see the previous lecture for details. Now, notice also that when the read pointer exceeds the wavetable length, we need to subtract the wavetable length. This is very much like what we did in the sine oscillator, where when it became greater than 2 pi, we subtracted 2 pi. And notice that we don't simply reset the read pointer to 0 when it goes beyond the end of the wavetable. That's because we may end up overshooting the end of the buffer by a little bit, and we want to make sure that we end up in the right place when we wrap around. One subtle point here is that we're using a while statement rather than an if statement to wrap around the buffer. Why is that? Well, imagine that we plugged into this oscillator a very large frequency, such that the read pointer went far beyond the end of the buffer after just one increment. We want to make sure that subtracting the wavetable length is enough to bring G-read pointer back into a valid range, otherwise we'll access a piece of memory that we don't own and our program will crash with a segmentation fault. There are other ways of wrapping the read pointer around at the end of the buffer, things involving modulo arithmetic, which we'll see later on in this lecture series. Now there is one problem remaining with this code, and it's right here. Can you see what it might be? Well, G-read pointer is declared as an int. An int is a type of variable that holds whole numbers and not fractions. So the problem that we might have is that to play at a particular frequency, the increment that we need each time might not be an integer. In this particular example, we have a table that's 512 samples long, and we wanted to play a frequency of 220 Hz at a sample rate of 44.1 kHz, and that works out to an increment of 2.55 samples each time through the for loop. So we need a float, and not an int, to hold the read pointer. If we use an int, the read pointer will always be rounded down to the integer just below its value. In this case, it's going to give us the wrong frequency, and we can actually work out what that frequency might be. Well, instead of having an increment of 2.55 every iteration of the for loop, we have an increment of just 2 samples, and then we can work that out from the same expression we saw in the previous slide. We would find out that we have a frequency not of 220 Hz, but of 172 Hz. So we have to make G-read pointer into a float. This then throws up another problem, which is that we can't use a float as an index into an array. And that's for two very good reasons. One is that from a code perspective, there's no meaning to asking for element 1.5 in an array when an array has discrete elements ordered one after another. It also doesn't make sense mathematically from a signal processing perspective. Digital signal processing involves working with signals in discrete time, which are mathematically defined only at integer values and not the values in between. So we've got something of a problem here. What can we do about this? Well, what we could do is keep the fraction in the read pointer all the way up to the point at which we read from the array, and only there do we drop the fraction off the end. So once gReadPointer gets to the point of being used as an array index, then we either round it down or round it to the nearest whole number and convert it to an int. But we only do this when we're accessing the array, and we make sure that we always save the fractional value in the float. So if you haven't done this already, then try it now. In the wavetable example, change gReadPointer from an int into a float. And to round it down, you can either use the floorf function, or you can just typecast it to an int by putting int in parentheses right before its value. Pause here, and then we'll look at it together. Okay, so here I have my wavetable example, which has been completed. You can see that read pointer has been turned into a float. If we scroll down here to render, we can see that this is the calculation for updating the read pointer, and here is one solution to turning read pointer from a float into an int so that we can access the array properly. And if I run this, we should see that it'll generate a triangle wave of the frequency that I expect it to be. Good. So this is the first step toward a wavetable oscillator. We saw that we could play a buffer of samples over and over again in a loop, and the way we set the frequency was by changing how much the read pointer advanced every frame. I want to switch topics for a minute and show you one of the features of Bela, which will be really useful for our programs going forward. The Bela IDE provides you an oscilloscope that runs in the browser. As the name oscilloscope implies, this is a way of viewing oscillations or signals. And essentially we're just talking about making an XY plot, where on the x-axis we have time, and on the y-axis we have the amplitude of our signal. And you can have more than one signal plotted on the same set of axes. And in the Bela oscilloscope, the signals don't necessarily need to be your inputs and outputs. They could be potentially any signal that your program generated. We'll see how to implement this in code in a moment. But just to get a sense for yourself of how the scope works, open the example project in Bela in the category called Fundamentals. The example is called Scope, and when you open that, you can click on the Run button in the lower left-hand corner to start it running. And then what you should do is click on the button in the toolbar that looks like a sine wave. This will open the Bela oscilloscope in a new browser tab. For this example, you'll see something that looks like this with 3 sine waves of different colors. There are a number of controls that you can adjust by hitting the Toggle Controls button in the upper left-hand corner. For example, you can change the horizontal scale, which shows how much time fits horizontally in the browser window, and you can change the vertical scale for each channel separately. Notice that we have separate vertical scales for each signal that we plot, but only one horizontal scale for all of them together. Just as a thought exercise, ask yourself why that makes sense that there would be only one time scale for everything together. Something else that's useful to remember is the default ranges of signals on Bela. Audio signals are typically between -1 and 1 at full scale. We'll later look at analog I/O on Bela, and that takes a range between 0 and 1, which would be the top half of the window. Again, you can use your scale controls here to make your signals bigger and smaller so you can see them appropriately. One other thing that we'll encounter with any oscilloscope is when the screen is drawn, and this is important to get a nice stable plot over time. The idea with the scope is that we are seeing regular snapshots of the signal drawn in this window. And if we don't handle it carefully, we might find that the snapshots start at a different point of the signal each time, which gives us a display that appears to jump around, sort of like this. The solution to this is something called the trigger, and what the trigger does is it lets us start drawing the waveform at the same position each frame, so that we end up with a nice stable plot like this. More specifically, what we're talking about is setting some sort of threshold or level, where every time the signal crosses that level, that's when the display starts being drawn. So you can see here in the Bela oscilloscope controls that we have a number of controls related to the trigger. The top one is the trigger mode. It tells us whether we should display the screen whether or not there's been a valid trigger received. If you use the normal mode, then the screen will simply stop updating until it next receives a trigger. That can be really useful for visualizing events that happen only occasionally. We can set which of the channels the trigger operates on, if there are multiple channels in the scope. We can set whether we want the screen to start drawing with a positive transition or a negative transition. And then finally we have the level, which is the threshold that the signal is expected to cross when the screen is supposed to begin drawing. To use the Bela oscilloscope in your code, you need to include the scope library. The steps are using the #include statement to include scope.h into your source file. You need to make a global variable of type scope. You need to initialize that variable in your setup function, telling it how many channels there are and what the sample rate is. And then finally, in your render function, you need to send the signals to the scope. We're using a method there called log, so you see here at the bottom of the screen, gscope.log, and then inside the parentheses, the 3 signals that we want to send to the scope. There are 2 forms of this log method. One of them has each signal as a separate argument, and the other has an array containing all the signals. The important thing to know is that you need to call log at the right rate, which is to say, it needs to be once per frame at the sample rate that you have specified. Now the Wavetable project also has support for the Bela oscilloscope, and let's have a look at that now. So I can run the project, I can open the scope here, and we can see our triangle wave visualized in the scope. I can go up here to toggle controls, and here we can do things like adjust the scale of the waveform. We could change the time scale, so we could zoom in and out in time. We could change the trigger level, so we saw that if the trigger level is outside the range that the signal takes, we stop getting a trigger and the screen starts rolling around a little bit. If we change from auto mode to normal mode, you'll see it stops updating at all because it's not getting any triggers. So let's go back to normal mode, or sorry, let's go back to auto mode, and we can see then we put the trigger back to something that we're actually receiving. We could change the trigger direction from positive to negative, and the screen inverts, and there's a few other minor controls that we can adjust as well. Now, I want to go back over here to the code, and I want to make a change from the wavetable length being 512 samples to a really short wavetable of only 16 samples. So we're going to run this now, and when we look at the scope, we're going to see something rather different. Finish building render.cpp, it's not going to look quite like a clean triangle wave anymore. Instead, we see this sort of stair-stepping. Why is that? Well, it's because instead of storing the triangle as 512 points over time, we only have 16 different points to represent the entire oscillation of the triangle wave, and we're seeing the stair-stepping really clearly here. The reason we're seeing the stair-stepping so clearly, if you recall, is that when we looked at gRead pointer, we just rounded off all the fractional values, and we read whatever integer value was the closest to it. So we end up with only 16 values that the triangle wave could take. So what should we do about that? In some applications, we'll be constrained by memory or other resources in terms of how big the wavetable can be, and we'd like to be able to get the best fidelity possible within those constraints. Strictly speaking, we are trying to read a fractional value from the array which didn't exist. If this was our read pointer, we couldn't ask for x of 1.6 because it simply didn't make any sense in the context of the array. But what we really wish we could do is look at what signal the wavetable was approximating, and then go looking in between the points there on that original higher fidelity signal. Now, what we're actually doing in our code is something like this. Notice this looks very much like the stair steps that we just saw in the Bela oscilloscope. We're always looking for the sample that is right before the read pointer, whatever its fractional value might be. So how could we do better? How could we get closer to that approximation of the original waveform? Well, what we could do is take a weighted average of neighboring samples, basically like drawing a line segment between 2 adjacent samples and then looking somewhere in the middle of that line according to where the read pointer is. So in this example, x of 1.6 would be calculated as 0.4 times x of 1 plus 0.6 times x of 2. And just convince yourself that it makes sense that it's this way around and not the other way, 0.6 times x of 1 plus 0.4 times x of 2. What we're talking about here is known as linear interpolation, essentially drawing a straight line between 2 adjacent samples by taking a weighted average. It's important to emphasize that this is not a fully accurate reconstruction of whatever the original signal might have been. To get an actual ideal reconstruction of the original sampled function, you would need a mathematical function called a sinc, which is not causal and is a problem to implement in any practical situation. So we can use linear interpolation, and it's much better than the nearest neighbor that we were using before, but there is still some degree of distortion. And for this reason, there are other more accurate approximations that are sometimes used, such as cubic interpolation, which uses 2 samples on either side rather than 1. This is discussed in a textbook that I wrote together with my colleague Josh Rice at Queen Mary called Audio Effects Theory, Implementation, and Application. But of course, there are many references for this online as well. Right, so to implement the linear interpolation then, these are the things that we need to know. We need to know the sample before and the sample after the read pointer, which has a fractional value. And then we need to know the fractional component of the read pointer's index. And that's going to determine what weight we place on the before sample versus the after sample. So let's suppose here that x is our signal, n is the integer part of the index, and f is the fractional part of the index. So notice the fraction ranges between 0 and 1, and that means that we can calculate x of n plus f according to the following formula. 1 minus f times x of n plus f times x of n plus 1. So x of n plus f in this case is a continuous signal which is being calculated based on a weighted average of 2 discrete time samples. So for example, x of 2.7 could be calculated as 0.3 times x of 2 plus 0.7 times x of 3. Now this generally works in every case except for if index n plus 1 is off the edge of the table. For example, calculating the value of x of 15.1 if the table only has 16 values. In this case, x of 16 is not a valid index into the array, so what should we do instead? Well, what we should do is wrap around to the beginning of the array so that x of 15.1 is a weighted average between x of 15 and x of 0. So that brings us to our next task. What I want you to do is implement linear interpolation into the wavetable example. And I strongly encourage you, like I did, to change the wavetable length down to 16 samples, because that will make it really obvious in both sight and sound whether your linear interpolation is working correctly. So pause the video here, see if you can make the linear interpolation work as code, and then when we come back, we'll look at it together. Okay, so your code might look something like this. I've pulled out the most salient bit, which is what's inside the for loop inside of render. And at the top we have gReadPointer. We can see that gReadPointer is going to have an integer and a fractional component, n plus f, like the slide that we looked at before. And the variable index below will give us the integer component using the floorf function. And then to get the index above, all we have to do is add 1 to index below. We do have to be careful that index above hasn't fallen off the end of the wavetable, so we check whether it's greater than or equal to the length of the wavetable, and if it is, we set index above equal to 0. Now into the second part of this code, what we need to do is extract just the value of f, the fractional component of this read pointer, apart from its integer component. And that's actually reasonably easy to calculate. We just take the read pointer, which was representing n plus f, and we subtract index below, which represented n. And so what we're left with is only the fractional component f, and we're calling that fraction above and storing it in a float. Then from there, calculating fraction below is quite easy. We just take 1.0 minus fraction above, and these are going to give us the 2 weights for the sample before and after the read pointer. So then finally we're able to implement the formula that we saw before. The output value is equal to the fraction below times the wavetable at the index below, plus the fraction above times the wavetable at the index above. And then notice that I'm scaling the whole thing by g amplitude just to set the overall levels. The incrementing the read pointer works exactly as it did before. There's no change there. It's just a change to how we access the wavetable. So let's take a look at how this goes. First of all, just for point of comparison, here's the old way that we did it, where we have just using the nearest neighbor interpolation. And if I run this code here and it compiles, notice that I have a wavetable length of 16, which will make it easy to see the problems here. So when we run this code, you'll see that it sounds rather awful. And if we look in the oscilloscope, there's our stair steps. Big problem. Okay, fine. So we'll stop that. And now what I'm going to do is delete this code here, which is the old way of doing things. So now we have our actual linear interpolation that we looked at in the slide just a moment ago. So we'll rebuild this project again, and we should see that when it runs, it sounds better, and that the waveform is of better quality. So we'll look over here at the Bela oscilloscope, and there we are. Our stair steps have been replaced with a nice smooth triangle wave, even though we still only have 16 samples in the wavetable. One last topic then for today is how we populate the wavetable itself. We could do this a couple different ways. We could load a sound file, as we did in the previous lecture, or we could generate a waveform mathematically. And we'll look at the second of those here. So let's suppose that the wavetable has a length of n. Then we have an array to fill, and the range of valid array indexes goes from 0 to n-1. And what we need to do is to write a for loop, which we can run inside the setup function, which is going to step through each of those array indexes and fill it with a sample value. And together these samples are going to represent one oscillation of the waveform. So we're going to have this for loop, it's going to start at 0, it's going to continue up to but not including n, and then we have little n++ at the end, which means increment n by 1 each time. And inside of here we're going to say g wavetable of n is equal to something, depending on what shape we want for our waveform. If you look at the wavetable example right now, you'll actually see that there are two different for loops, one after another. The reason for this is that we've made a triangle wave which spends half the table increasing and half the table decreasing. So notice that the first for loop starts at 0, goes up to but not including wavetable length divided by 2, and then the second for loop starts where the first one left off and goes to the end of the table. For most of your wavetable calculations, you can probably use just a single for loop of the form shown on the slide. So try this then. Change the setup function so that it has a single for loop going from 0 up to g wavetable length and calculates a sine rather than a triangle waveform. And the tricky bit here is working out how to use the value of lowercase n to come up with the phase of the sine wave. And to do this, you'll probably need to go back and look at some of the phase calculations from lecture 1 in this series. See if you can make this work. So here's one possible implementation of that. You can see that we are calculating the wavetable as the sine of 2 times pi times n divided by the table length. Basically, the idea is that when little n reaches the end of the table, we want to have gotten to a phase of 2 pi so that we have one complete oscillation of the sine wave inside of this table. And notice that I'm typecasting both n and g wavetable length as floats, just to be really clear that we don't accidentally end up dropping off the decimal points in this computation. In this particular case, I think it should work fine whether or not you have this float here or not, because both 2.0 and m_pi are already floating point. So if we build and run this, then we should see that instead of the previous triangle wave, we have something resembling a sine wave. Now, if you look here at the scope, you can see it's not a perfect sine wave, and you might remember the reason why. The reason why is that up here, we set a wavetable length of only 16 samples. That's not a very good approximation of a sine wave, although we're doing all right because we have this linear interpolation, and you can in fact see the straight line segments connecting one sample to the next. Probably if we want a really nice sounding sine wave, we ought to have a longer wavetable, so let's go back to 512 samples, try that again. And we'll still leave the linear interpolation on. So this should be a relatively high quality oscillator at this point. All right, there we go. And look at the wavetable, and now you can see it's a much cleaner signal. Let's try one last thing before we wrap up. The point of doing a wavetable, in part, is the flexibility in the kinds of waveforms that you can calculate. And if we're just going to use it to make a sine wave, then it somehow doesn't seem all that exciting. What we could do, though, is we could build up a more complex waveform by adding several different harmonics of a single fundamental frequency. Now, this is a process known as additive synthesis, and we may talk about this more later on, and it can certainly occupy several lectures all on its own. But essentially the idea is building a complex sound out of simpler parts, and the way that we're going to do that in this case is having a series of sine waves whose frequencies are integer multiples of one another. And as long as they're integer multiples of one another, we can fit them into a wavetable like this. So here's the function that I propose that we implement and store in the wavetable. And what I'm going to do is just show you how it builds up piece by piece and what it should look like when it's all done. So this function, w of phi, is going to be equal to 0.5 times sine of phi, that's our fundamental frequency, plus 0.25 times sine of 2 phi, so that's our second harmonic at a lower weight, plus 0.125 times sine of 3 phi, our third harmonic, plus 0.0625 times sine of 4 phi. That's our fourth harmonic. And all of these, when you add them together, end up looking something like this. a sort of very approximate sawtooth wave. The point is that you could choose any weights and, in fact, any phase offsets of these sines you want as long as they are integer multiples of one another. So see if you can make this work in the wavetable project to calculate not just a single sine wave, but this mathematical expression and store that in the table. You should be able to use the scope to find out if it works as you expect or not. Pause the video here and we'll look at this last thing when you come back. Okay, so here we are then. You can see that I've written out the calculation for g wavetable of n as the sum of those 4 sine waves in the weights that were specified in the slide. And notice that I've done here twice the frequency, 3 times the frequency, and 4 times the frequency. Now, you might well look at this and say that's a giant waste, 2.0 times 2.0, why not just write 4? Of course that's true, you can do that. It's not going to be any computational cost here because the compiler is going to optimize this into a single number. So if this makes your code easier to read, you can obviously do it this way instead. Notice also a feature of the C++ language, which is that you can have single statements which break across multiple lines as long as there's no semicolon, because it's the semicolon and not the new line that tells us when a statement ends. And so writing it like this actually makes it a lot easier for your code to be read than if you had one really big long line there. So if we run this code, we should hear a different kind of tone. And if we go to the oscilloscope, we should see that we have a waveform that looks approximately like what we expected based on the slide. So there we go, an example of a wavetable oscillator that we calculated as a sum of different frequency components. There's lots of follow-up you can do here, and hopefully now that you have the tools to do this in C++, you can go find other computer music tutorials and implement them for yourself. That's it for today. Starting next time, we're going to look at some ways of controlling the parameters on your Bela projects. In the meantime, you can find us in all the usual places, on our social media at Bela Platform, at our forum where you can get support, our blog where you can see projects that have been made with Bela, and the knowledge base at learn.bela.io where you can find more tutorial materials. Thanks very much for following along. Don't forget to click subscribe so that you're notified of each new lecture as they become available. See you the next time.